Okay, hi. Starting the second lecture, this is on standardizing variables. And this would be 7.5 in the textbook. Um, there's So what this means is we get our data set. We identify a column as the response, and several or one of the other columns or functions of the other columns as predictors. And sometimes it's desirable to first transform the data uh, to make a transformation on the data. So this is actually, not strange to you. You've done things like normalized vectors. Sometimes when we make a PDF, we have a function that we want the shape for the PDF to be, and then we divide by the integral under that curve so that it's normalized to 1. So things like this are common, and there's several reasons why you might want to change the variables and standardize them. It doesn't lead to changing the inference, but it can lead to an easier way to understand things, and it can clarify certain side effects and other properties of the data. So there's two reasons. So maybe I'll just start with two reasons that we can think right away to do this. There's more probably. One is to reduce numerical side effects. And two, for comparability. So rather than talk about them now, let's go into them in detail, just a little bit of detail. So first, one, what this means is that really has to do with finding the estimated regression coefficients. At one point, we are taking an inverse, and this is a pretty heavy numerical operation when we take the inverse of xtx, especially depending on the size of the number of predictors and the size of xtx. So let's see, xt would be p by n, right? And x would be n by p. So it's p by p. And, even a 10 by 10 matrix could have side effects. So here's an example of side effects. Suppose I have the system, so compare. Suppose I have something like x plus 1,000, y equals, and suppose I have 1,000. Y equals 1,000. Well, then the solution is equal to, can you see the solution? Y is 1, so x is 1. So x equal 1, y equal 1. Okay. Now, suppose I change this slightly. Maybe I just, slight error in the data or something, or some round off problem or something, and I instead have this one. And say this is equal to 1,001 again, and now this one's 1,000, y is equal to 1,001. So all that happened is this went from a 0 to a 1 way out here. Okay, so not much difference between, say, $1,000 and $1,001. But so say I have this equation now, and I'm trying to solve that. What's the solution? Well, you can read the solution again. I have y equals 1.001 on the bottom there. But then that means x equals 0. So we get a very different answer for x. And this is problematic. Here's another example. So here's an example. So let's write the word but. So you see that this is a, so slight change in one place leads to a drastic change in another. And this has to do with the order of magnitude being quite different. So this is caused by order of magnitude of x coefficient being much less than of y coefficient. Okay, here's another example. So another thing is consider as well another example. So suppose we want to take the inverse. Suppose a equals, I don't know, let's think of something like, let's say, doesn't have to be anything too clever. Say it's 0.001 and 1. Let's make this actually 0 and 0.001. So this has an inverse. I'm not going to compute it. So we could solve ax equal b. But you can see if I had a prime, say, equal to, and this just changed from 0.001 down to 0. This does not have an inverse. Okay, so no solution to. In general, right? There might be a solution. So unless b equals like some multiple of 1, 1, or something like that. Okay, so you can see this thing of different magnitudes here. You know, here I have 0.001, here I have 1. This can lead to numerical effects. Standardizing the variables can deal with this. Okay, so this is one reason. The second reason, comparability. So what does this mean? So suppose, so for comparability, what it means is that with greatly different magnitudes of predictors, it can be tricky to look at the regression function and determine, to get an intuitive feel for what the regression function means. Okay, so let me see. Good Lord, taking a long time. Okay, so let's just write different orders of magnitude in predictors can make regression function more difficult to interpret. Okay, I had this example. So, for example, from our real estate data, suppose we had y is price house price, USD, and let's have X1 be square feet. I don't know why I put the units of the building. X2 is, say, whether an indicator saying whether it has air conditioning. So AC, 1 equals yes. Whether it has central air conditioning, 0 equals no. You wouldn't really care, right, if the house had an air conditioner in it. It means central air conditioning. Okay, so what could be the problem here? Well, say typical price here might be, so typical order here might be around, let's see, something like 10 to the 5th, right? Something like this. So say around 10 to the 5th, maybe 10 to the 6th. And here, the square feet of the building, let's see, this is going to be around 10 to the 3rd. So these are constants times these, something like that. So maybe your house is, I don't know, worth $250,000 and it's 2,000 square feet, something like that. Okay. That would be nice, right? All right, so we actually did this with R. So using R with the data we had, we found price. I found price was equal to, I got minus 95, 450. That'd be a good price, right, for a house. Minus 95, 450. They give you $95,000 and you get the house too. Plus 155.1 building. And then plus 27,367 AC. Okay, so this is for the example from the book. Oh my God. Okay, just to finish up this, and then we'll start another one. So one thing is the building's in square feet. We can readily understand this means basically that having central air adds. Now, there's a lot here actually. So what this really means, if we're super careful, it just means this is the fitted line. So this means all else held equal, having air conditioning versus not having air conditioning will tend to increase the price, on average statistically along the fitted plane by $27,000. Okay, that's all this tells you. It doesn't say this is really the way the system works. It's just saying the fitted plane works this way. That's one clear and careful and important distinction to make when you read these coefficients. It's for the fitted plane or the fitted line, fitted hyperplane. And this one says, okay, each square foot of the building increases the price by about $155. Okay, so then you could kind of compare these two and say, well, how many square feet are equal to having central air conditioning? And I think all you need to do is divide these two coefficients, and you would find you would have roughly about 180 square feet is equal to central air conditioning, something like this. But remember, this is only along the fitted line. Okay, still, you'll admit, this is a little hard to look at and see which one's important, which one's more important, which one might be not as important. So one thing we can do is standardize the variables, and that will make it a little more clear right from the equation how to compare different predictors. I mean, this is pretty simple too. It's just these three variables. And if I have many, it might be nice, and some can be more confusing than this, it might be nice to have them all standardized. So we're going to get into the details of that next. Thanks.